Hi everyone. So now it's on the course. So let me continue what we talked about on the Tuesday. So on the Tuesday we mentioned in general there's a heat equation regarding it's in the constant coordinate or cylinder coordinate or spherical. Then you can use this kind of equation, and then as long as you put it into the right numbers of the n. And if you're talking about a constant coordinate, then the n will be 0, and then you substitute the r into x. Then if it's a cylinder coordinate, then the n will equal to 1, and then you stay the r as the r as well, and then the spherical will be 2. So this will be the general heat equation which can adapt to different situation. So now if we take a look, let me take a look. If we have a close look at this heat equation, then you can find this actually is a PDE, and as you can see here, there's a PDE here, and there's also a number. Even though we get rid of the constant of the heat generation of the K, then you still have the PDE. So we will need a boundary condition and the initial condition to help us to solve the issue. So it's quite similar with the fully developed flow in the tube. Then this is also Navier-Stokes equation is a PDE, but at certain boundary condition and initial condition, you are able to get rid of certain term. Then you can find the constant you want, and then to find a solution. So here we are going to introduce the boundary condition and initial condition in the heat transfer. So let's start with the boundary condition and initial condition. So let's assume first we don't have the heat generation. That would be easier. So we assume no or without Q generation. Okay, so in this case we will demonstrate 4 different kind of a situation without heat generation. So the first one, so but before that, let me write it down, the heat equation again, but without the heat generation. So the equation will become the partial T partial X. It's one direction, okay? It's a one direction, and equal to as alpha delta T. Okay, so by looking at the equation, so you know here we will need 2 boundary condition which is have a relationship with x term. Okay, let's write it down like this. And by looking at the right hand side, this will be, we need at least one initial condition which is relevant to the time, the delta, the t. Okay, so as long as you have the boundary condition and initial condition, then you can solve the equation. So the first one we are going to introduce is Dirichlet condition. Let me write it down. Dirichlet condition. Okay, so what is Dirichlet condition? Actually, it's quite easy. So let me roll down the axis. So this is T, this is X. So you have a wall here. Then you know the surface temperature T1 and another side T2, for example, like this. So the boundary condition here is very easy. So the T x equal to 0 will equals T1. Tx equal to L, oh, this is L, equals T2. So this is your boundary condition. Okay, that's the first one. So the second one is Newman condition. The Newman condition means you have a specific surface and then it has a heat flux. So slightly different from the Dirichlet condition. So the Dirichlet condition, it means you have a surface and then you know the temperature of it. Then the Newman condition is you have a surface and there's a heat flux going through the surface. So let me write it down, draw it down the figure. So it will look quite similar to the Dirichlet system. Then Tx, but here we have heat flux Q here. Yeah, so this is not heat generate on the surface. Instead of generate the surface, it's just a heat flux going from the left hand side to the right hand side. So the boundary condition will be writing down like this. So the boundary condition will be using the Fourier law. So the heat flux will become minus K partial T partial X, and at which position? At the wall, so x equals to 0. Okay, so this case is quite similar to you want to put something on the electromagnetic oven to heat up, then this will be a case. So the wall itself or didn't generate the heat, but there's a heat flux across the interface. Okay, then the third one is the insulated case, but it's called adiabatic. Let me pronounce adiabatic. Yeah, adiabatic condition. Okay, this is also let's write it down in Mandarin. Okay, so you can imagine same system X T, and then you have a wall, and this wall is a insulator. Okay, so this one is slightly complicated, but if you imagine there's a wall as well, then you want to know what's the temperature on this surface and to another surface, then it could be the temperature profile look like this, right? For example, it cool down, or maybe it heats up. So far we don't know. Okay, but there's a very characteristic phenomena in this insulating wall system is at this insulating wall, at the point of the interface here, the slope will be 0. So here, let's draw it perfectly like this, and the orange one will be like this. Okay, so this will be, the slope will become 0. Okay, 这里的斜率会是0。Okay, so here and here. Okay, slope will equal to 0. Okay, so the boundary condition will be partial t partial x, where x equals to 0, then this will equal to 0. So this is the turn of the slope. Okay, it's because of the wall is insulator, so the temperature won't change at that point. So at the precise point at the wall, the slope or the temperature won't change. So the slope will become 0. So this is the boundary condition with adiabatic condition. Okay, then we move to number 4. Number 4 we call Robin condition. Okay, the Rubin condition actually we already mentioned at the end of the chapter 1, which means you have a wall and another side you have a surface convection. Okay, so let's draw it like this. Then you have a wall and you have a convection here. Then you know the H, or maybe you don't know, and then you know the environment temperature. Okay, so in this case, the boundary condition will written down like how the heat going to conduct from the left hand side to the right hand side, right? So it's the first law of the thermodynamics. So minus K, Fourier law again, x equal to L at this surface, at this interface. Okay, then the conduction will equal to convection, so the H times the x equal to L minus the environment temperature. Okay, so those four are the case generally without heat generation. Then you have Dirichlet, Newman, and adiabatic and Rubin condition. Okay. Okay, then we are moving to something symmetrical. So, for example, it's easier to start with the drawing. X and T, then you have something here. Then by looking at the temperature profile, you found the temperature profile look like this. Then you probably can suspect here we have convection and another side has a convection as well. So here we have H and H. Okay. Then by looking at this figure, then you probably notice the maximum temperature will be here in the middle. So here will be partial T, partial X equals to 0. Okay, and usually if you found this kind of temperature distribution look like this kind of parabolic profile, which indicate it must have a heat generation inside of the system. So the wall itself have a heat generation inside. So that's the reason you observe the temperature profile look like this. Then we write it down the Q generation here. Okay, this one actually is quite similar to the fluid dynamic. If you recall, the one you doing the Navier-Stokes or fluid development flow in the pipe, then if you have a pressure gradient, then the velocity is parabolic. But if you don't have the pressure gradient, then the velocity is linear. Okay, let me recall a little bit. So in the fluid dynamic, so if you have delta P, then in the pipe flow, then you will have a parabolic profile. This is your V. But if you don't have the delta P, then this will become the quick flow. If you remember, this will be a fixed plane and this one will be moving. Then the velocity profile will look like this. So in this case, the velocity profile will be linear. But if you have a pressure drop or you have a pressure gradient, then the velocity will be parabolic. Okay, so this is quite similar with the heat transfer. If you have a heat generation, the temperature distribution will not be linear. It will be either parabolic or like a slightly complicated polynomial condition. Okay. So you just remember, if you see something, the velocity profile is parabolic form, then you will need to know they might have the heat generation inside of the object. Okay. Okay, this is the one with heat generation inside. And since they have convection at both sides, so the temperature profile will look like this. So this will be low. This will also be low because the convection get rid of the heat, and then the maximum temperature will be at the middle. And this is symmetrical. OK， 是对称型的哦，有发热的，所以它跟流力非常相似。在管流当中，你只要有压力梯度，你的 V 你的 velocity profile 就是抛物线。那这个抛物线可能可以长得很奇怪，但它一定会是二次的形式。那如果你的 V 是线性的话，那就表示说你这个液体的流动驱动的力不是因为压力。那在流体力学当中，我们讲的不是用压力梯度驱动的力，那只有一个 case 就是 quick flow， 就是脱液流动，或者是你这个脱液流动也可能是在润滑当中会出现，例如说通轴，然后你外面包裹了一层 lubricant 润滑油，然后你只有中间轴转，然后外面的 housing 不转的状况之下，那它中间也是一个脱液流动的一个状态。那热传就会跟流力的 case 非常非常的像，所以你现在只要想有压力梯度跟有热源是一样意思，只要你看到 velocity profile、temperature profile 有是抛物线的形式的话，那就表示说它一定有热源的产生。Okay, so let's move to another case we called perfect contact surface. The term might be slightly different from in the textbook, but once I draw the figure, you will know. So, for example, we have two material. This is A, and another one is B, slightly shorter. Then, in between of their contact interface, let's slightly zoom in, will look like this. So you have Q conduction from not necessary to be a conduction, but let's just assume this is conduction. So QA will equal to QB because it's perfect contact surface. So all the temperature or all the heat will going to transfer across the interface. So the boundary condition here, we can assume when x equals to LA. Okay, we should write it down like this. And this would be LB. And they have its own K value because conduction. Okay, so come back to the boundary condition. When x equals to LA, there will be two boundary conditions. The first one is the T must be the same. Is the same. Okay, so since it's a perfect contact surface, so we can try to draw a temperature profile. For example, it starts from here, then reach to the temperature. But because of the K value is different, so the slope might be different. So let me easily draw it like this. So this will be Tx. Okay, but because of the perfect contact interface, so at that point, the T will be the same. Despite this is in the perspective of A looking towards to B or B looking towards to A, the temperature should be the same. Okay, so in this scenario, then we can write it down. the TA at x equal to LA equals to TB x equal to LA. Okay, then the second boundary condition will be the heat flux will be the same. So the heat flux is the same. Okay, so then we can also write it down by the Cooling law. Not the Cooling law, sorry, the Fourier law. Okay, partial T partial x equals to LA minus KB partial T partial x equals to KL. Okay, so this will be our boundary condition for the perfect contact surface. Okay, so then now I still need to remind you something similarity between heat transfer and thermodynamic. So if we recall a little bit, so the quick fault we just mentioned, there's a more advanced system is if the quick flow contained with two different liquid with two different viscosity. For example, we do it like this. Then we have a liquid have viscosity called A, another viscosity we call B. Then the thickness of the liquid is the same, so it's L and L. And this is X direction, this is Y direction. And then because it's quick flow, which means we are going to drag the platform in from left to right, and the bottom one will be fixed without moving. Okay, so now we want to draw the velocity profile. This will look like this. Okay, so we will start from the non-slip condition. So this will be, for example, this will be like this, but at the interface, it will suddenly change because the viscosity is different. Then we can draw it like this. Then this will be our velocity profile. Here, this will be our velocity profile. Then you can notice the viscosity is different, so the slope is different. So the mu A then equals mu B, and the slope is different. Okay, so if you recall in the fluid dynamic, we can write it down the velocity profile at this position and this position. Let me write it down. So the UA at Y will equal to C1Y plus C2 because it's linear. Okay, there's no pressure gradient, so this only the quick flow. So this the velocity profile will be linear. Okay, and the bottom one will be UB Y, then we C3 Y plus C4. Okay, so that's the boundary condition of the fluid dynamic. You might find it's quite similar to the one we talk about, the perfect contact surface, because now we are going to write it down this boundary condition. So when the Y equals to L in the middle plane, then the first one, the velocity should be the same because it's continuous, right? So the UA Y equals to L equals to UB Y equals to L. And the second will be the shear stress is the same. The shear stress is the same. So we took the definition of the shear stress, partial UA X. Oh, nah, it's Y in this direction. that y equals to L equals to mu b partial ub partial y equals to L. See, those two are very similar to each other. Okay, that's something I'm keep talking about from the very first class. Heat transfer have a lot of similarity with the fluid dynamic. Okay, so this is just to record you of the fluid dynamic, but it's quite similar to the one we are driving here right now. Okay, so if there's a case with imperfect surface, let's just use this space here. So we have material A with a defect, and this is a material B here. Then they don't have the perfect contact interface, but in between of the space here will kind of full of what? For example, we're full of air. Okay, let's write it down. Okay, this will be air inside. Then air is a perfect heat insulator. So which means if we have a close look at this area, then the QA, QB might not be the same. Okay. So you might want to ask, if the QA didn't equal to B, then we lost one of the boundary condition. Could we still find it out how much heat is going to transfer across that interface, even with such heat insulator in between? Yes, we can do that. In the later chapter, we will introduce something we called contact resistance. So our heat contact resistance. So this will acting like in the electric circuit. Then you have a resistance. Then you need to overcome this resistance. So for example, if the RC, the thermal, the resistance of the conduction is really high, which means it's not easy to pass the heat from one interface to another. But if the RC is relatively small, then you can consider it as a conductor. Okay, but the RC is not something you can directly check in the table. It can only obtain from the experiment. So it's only obtained from experiment only. Okay. So if it's an imperfect surface, we need to find out the resistance in between. Then by running several experiments, then we will demonstrate or we will describe in the later chapter. Then as long as you have the RC, then you still can calculate how much heat is going to transfer from the left hand side to the right hand side. Okay. So far so good. Okay, let's take a break.